gonna resume class. And before break, we were talking about the limitations of the dynamic lamp that has been used in computer system. We have seen that it has a problem with the internal chip architecture, and a slower interface to the processor is memory bus. And we thought about having different solutions. One, adding a static lamp cache between the central processing unit and the main memory. But this is not the right answer. This is not the right solution for this problem because of the price of the static lamp. And we talked about increasing the cache size. The cache size is fine, but it may have a negative impact of the overall computer system. So instead of focusing on adding a static RAM cache between the central processing unit and the main memory, or increasing the cache memory, the most improvement, the best solution is to focus on the DRAM itself, not on the adding static RAM cache between the central processing unit or increasing the cache memory size. Now, focusing on the DRAM itself, we have to talk about another type of DRAM that we call synchronous DRAM. It is widely used in modern computer systems. Unlikely the traditional DRAM, it has external clock which is being used to coordinate the data transfer. And it runs in synchronization with the processor as well as the memory bus at a full speed. So this is what we are looking for. We are looking for a full speed between the central processing unit and the main memory. So this, we avoid the wait state of the central processing unit, which has been observed when using the traditional DRAM, because the data has to be transmitted in coordination with an external clock signal with the central processing unit. Now, how does the traditional DRAM works? We need to first understand how the traditional DRAM works so that we do understand how the synchronous DRAM works. We have the central processing unit, which needed to transmit an address as well as a control signal to the memory system. Then the memory system, in this situation, is the DRAM, needed to perform some internal operations. Internal operation including the low or the current activation. If you still remember, when we talked about the memory organization, we have the memory organization which include many words. We have the memory organization which include many words. Now, this is the memory organization. Is a square array. We have the first word, the second word, the third one, and so on and so forth. Then we have the columns, the cells. We have the cells, we have the cells, we have the cells, then we have the cells. Now, let's say this is the word number 1. Word number 2, then this is 512, then we have 512 as well here. Now, for the DRAM, it has to perform some internal operation using the colon and the low address slope. The low address slope needs to latch a low, and the colon address slope needs to latch select a cell once the low has been selected. So that means the system needs first to select a word out of 512 of weight in this situation. Then once a word is selected, let's say we have a word one that is selected, then we need to have a specific cell selected to return a block within this cell. So this is how the traditional DLAM works. Now we have the access time, which delay, and it forces the CPU to be in what we call a wait state. And this waiting time will throw the overall computer system. We store the overall computer system. Now, because of the waiting time of the central processing unit, we have the delays, and these we have a negative impact on the computer system is performance. Now, to solve this issue, we have the central processing unit, which send instruction and the address to the synchronous DLAM. Since the synchronous DLAM has a external clock signal, we have the synchronous DLAM that needed to latch the request, and the data needed to be transferred after a fixed number of clock cycle. Because the central processing unit and the the synchronous DLAM, they are in coordination with the external clock signal, the central processing unit will know that the data will be returned within a fixed number of clock cycles. That means that the CPU can perform other tasks while waiting for the data to be returned to the central processing unit. And this will improve the overall computer system and its concurrency. So this is how the synchronous DLAM works. The central processing unit needed to send the instruction and the data. Then the synchronous DLAM needed to launch the request, and the data will be returned within a fixed number of clock cycles. And since the synchronous DLAM and the central processing unit, they are working in coordination with external clock signal, the central processing unit will know, okay, I have made a request of the data from the synchronous DLAM, and it's going to take a number of clock cycles. Then, because it knows the waiting time, instead of being in wait state, the central processing unit will be handling some other task while waiting for the data to be returned to the central processing unit. And this will help to improve the overall system computer performance efficiency. Here we have a 256 megabyte synchronous DLAM. As you can see, it includes the command decode clock generator. Here we have the clock signal. We have the low address strobe to latch a low, and we have a colon address strobe to latch a colon, and then we have a write enable for power management. Then we have the data pins A10 up to A0 up to A10, and we have the BA0 and the BA1 pins for bank selection. Because the synchronous DLAM has a multi-bank architecture, we need the bank addresses. We need the bank pins to select a bank that needs to be used. Then we have the low that needs to be latched, use the low address strobe. Then we have the mode register. We have also the colon address latch because of the colon address strobe. And we have buster counter, how many buster are being fetched by the synchronous DLAM. Then we have low address buffer. Then here we have bank control logic because we have the synchronous DRAM, which include a bank, multi-bank architecture. Then we have data in buffer and data that comes out of the buffer. So this is the memory cell array of 256 megabyte synchronous DRAM. So what you needed to know is that it does use a multi-bank architecture, and also it has an external clock signal to be used in coordination with the central processing unit. And when the central processing unit made a request of the data, with the coordination of external clock signal, it will know the data will be returned within a number of clock cycles. And instead of being in wait time, the central processing unit will be in handling other tasks while waiting for the data to be returned by the synchronous DLAM. Then we have here the internal logic of the typical 56 megabit synchronous DLAM, which use a burst mode to improve the data transfer efficiency. We have the burst mode that needed to eliminate, and it has some setup low and colon precharge delay after fast access. So how does the burst model works? It does work as follows. We have a faster data item which is accessed, and the remaining data has to be returned in less time. Once the first data item is returned, it is quite easy for the system to return the next sequence of the data. So it is more effective when we have sequential data. We have a very big data that needs to be returned in a sequential order. For example, we have this memory system which includes 512 words. Now, if the system needed to return the first word, the first data blocks in the first word, that means it is very effective because the data is in a sequential order. So that is what I said. It is in the same law of the memory. If the data that the system wanted to fetch is in the same, we have data here. This is data. We have 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 the data. We have the data. If the system wanted to return the data in this law, that means that it won't take a lot of time, because it is more effective when the data is sequential. Next, we have the DRAM, which include multi-bank architecture, as I said, which we enable internal parallelism. It will enable the internal parallelism. As you still remember, if we have the data which is arranged into multiple banks, we talked about this in multiple banks. The central processing unit can have fetch in multiple banks at the same time. Now, let's say this is the bank 0, and this is bank number 1, and this is bank number 3. And this is the next bank. That means that here we have the central processing unit which can fetch the data in bank 0, and it does not have to wait until the fetching in bank 0 is done to get the fetching in the second bank. That means the data can be fetched from all the 4 banks at the same time. So the synchronous DRAM has an improvement over the DRAM because of this multi-bank architecture. There are many reasons for having this synchronous DRAM improvement over the traditional DRAM, but one of them is that the synchronous DRAM includes a multi-bank architecture, which enable an internal parallelism, which enable the system to fetch data from multiple banks simultaneously. Now, there are the mode register and the control logic of the synchronous DRAM. This allows the customization of the synchronous DRAM behavior. For example, the programmer can have to configure the system parameters to allow the synchronous DRAM to be customized. For the model register control, we have the bus length. That is the number of data that can be transferred per bus. So we have, in this case, we have 4 bus length, and the latency is the time that the system spends between the read request and the data output. How long does it take for the system to return the data from the time that the system has made a request to the time that the system return the data. So for the best performance of the synchronous DRAM, we have to get a very big data, but well, the data can be accessed sequentially, while the data can be accessed one after another. So it has multiple operations, multiple applications, including the multimedia processing, including the word processing and other applications as well, where we do have very big data which is arranged in sequential order. Now, likewise, other memory system that we do have learned, this synchronous DRAM also does include pins. So we have the address pins. Here we have the pin A0 up to A13. Here we have the pins A0 up A13. Then this pin is very important for low and colon selection, because as we have seen, the low address slope is there to large a low. So we need this pin for low and colon selection for the synchronous DRAM. Now we have the bank address lines. The bank address lines is very important because the synchronous DRAM has a multi-bank architecture, so we need the bank address lines to select a bank. Now, the next pin is the clock pin. The clock input, this is very important for synchronization operations. We need the clock signal to be activated to allow the synchronization of different operations. The next pin that we need to discuss for the synchronous DRAM is the clock enable. The clock enable pin is for the power management. The next pin is the chip select. For the synchronous DRAM, it is for activating the chip. Then we have the low address slope to large a low address. Then the colon address slope pin is to large a colon address. The next pin is the write enable. The write enable, which is there to read or write a control. Now, the next pin is the data input. The data input, which has 8-bit data bus, and we have also the data mask pin. This is for selective read or write operation. The next thing that we needed to talk about is the synchronous DRAM read timing. Here we have the clock, which include the following timing: T0, T1, T2, T3, up to T8. Then we have different commands, which include the read A, no operation, or we have here the data out A0 and the data out A1 up to A3. So this is the synchronous DRAM read timing with a bus length of 4 and the colon address slope latency of 2. Now, a timing diagram that is shown here is to depict signal levels that change over the time. So the most important thing that to note here is that we are talking about levels. High levels 1 and low levels 0. Then we needed to talk about the signal transition. 0 up to 1, that is the leading edge. 0 up to 1, we have the leading edge, and 1 to 0, we have the trailing edge. These transitions takes very, very small time, and often it is exaggerated in diagrams. We see here that these transitions are taking very, very less time. We have to talk about the levels, high levels or low levels. The most important thing is not paying attention to the values here. We do talk about which level it is. So we have different times which is in coordination of the clock. Now the next one, we have seen that the signal can be grouped using multiple bits. Example, we have seen 8 lines for 1 byte. So the focus is on the signal, not the exact value. As we have seen, we have a burst length of 4 and the current address slope latency of 2. We need to have the burst lead command condition, the current slope and the current address slope. For the low address slope, we have the right enable, which has to be set to be high. Now, we need also to provide the address input, which needed to specify the colon address. Which colon address? What is the starting point of the colon address? So this is very important to note that for this synchronous DRAM, the most focus is on the signal, not on the value themselves. Now, there have been some improvement of synchronous DRAM over the traditional DRAM, but there are also some limitation links with the synchronous DRAM. The synchronous DRAM improves on synchronous LAM, but there are still some limitations. The synchronous DRAM has some improvement over the asynchronous LAM, like the DRAM that we talked when we started the memory system lecture. So, but this synchronous DRAM does not achieve good result when it comes to the input-output data rates. So there was another introduction of the double data rate DRAM to solve the issue faced by the synchronous DRAM when it comes to the data, the input-output data rate. It was developed by the GDIC Solid State Technology Association, and this address needed to limit, and it is widely used in computers and servers. Now, how does DDR increase the data rate? Normally, the DDR stands for double data rate, DDR, double data rate, DRAM. That is DDR, DRAM. So data transfer needs to be done on both rising and falling clock edge. That needs to double the throughput. It has to use a higher bus clock speed, and it has also to use what we call a buffer or a prefetching technique to improve the data flow. Now, the limitation of the synchronous DRAM is that it does not achieve higher data rate for input-output. Then there was a need of the introduction of the double data rate, which has to use both the rising and the falling clock edge to improve the data rate when it comes to the input-output. which use a technique that we call a buffering or a prefetch to improve the data flows. Now, for small caches on the synchronous DRAM chip, we only have to fetch multiple bits per access. So this has to bridge the slow DRAM calls and the fast input-output interfaces via what we call parallel access and also serialization or multiplexers. We have to enable continuous high-speed data transfer to achieve higher input-output data rate. So how does the prefetch buffer concept works? We have a small cache memory on the synchronous DRAM, which has to fetch multiple bits at the same time. So this needed to bridge the slow DRAM call and faster input-output interface via the parallel access. It has also to enable the continuous speed data transfer. Here we have different generation of double data rate, right? We have different generation of the double data rate. We have the synchronous DRAM, which only rely on one bit, and here we have the memory array, and the input-output data rate is between 100 and 150 megabytes per second. Now, with the DDR1, because it does use 2 bits per prefetch, that means we have the effective data rate that needed to be double. We have which use the DDR1, which use 2-bit prefetch. We have 2-bit prefetch, 1, 2. Then we have a multiplexer. We see that the input-output data rate has been improved almost double, from 200 up to 400 megabits per second. Now, the next generation of the double data rate is DDR2, which use 4-bit prefetch. As you can see, we have a multiplexer. Then we have the input-output data rate, which has been almost improved triple. We have the data rate, which is between 400 and 1066 megabits per second. So this is very important to note that with 4-bit prefetch, we have 4 times speed up. For DDR3, it has how many bits prefetch? It has 8-bit prefetch, and the data rate for input-output is between 800 and 2133 megabits per second. This is for the DDR3. For DDR4, there is no change of the number of bit prefetch. We have 8-bit prefetch, likewise for DDR3. The only thing that has been improved is that there is the introduction of the bank group for parallel operations. This will allow higher performance without having a very big buffers. Now, we have 8-bit prefetch, but you see there is introduction of multi-banks, which allows the parallel access, and it does increase the input-output data rate, as you can see depicted by this table. So these are the generations of the DDR double data rate memory. Then the next one, we needed to talk about the trend off of the DDR. We have larger prefetch increase minimum buster length, and this has a drawback of reducing the flexibility of the memory system. Bank groups in DDR4, this has to mitigate the problem faced by the previous DDR generation by allowing the parallel activity across different groups of the memory system, which has to improve the system, computer system performance by allowing multiple operations at the same time. Now, we just done with the introduction of the synchronous DRAM, the double data rate DRAM. Now we needed to discuss about another internal memory system, which is the embedded DRAM. The embedded DRAM here is another type of DRAM memory which is integrated on the same chip, or it is on the ASIC of the microprocessor. So we need to have a memory size which is bigger than on-chip static RAM, but has to be smaller than enough DRAM for the same area. So the cost per bit is higher than external DRAM, but it has to be lower than a static RAM. How about the access time? The access time for this type of memory, the embedded DRAM, needed to be lower than the static RAM, but faster than the off-chip DRAM due to the proximity and wide buses. So this is the EDRAM. So how does it work, or how it does the fabrication is made for what? The EDRAM fabrication. We needed to talk about is fabrication. It uses different technology, but it has to follow the standard DRAM memory that we discussed before. Its design as well as its architectures. Now for larger system and high-end applications, these have a flat and wide spatial locality curves, and they make the DRAM-based cache attractive for their bit density. On chip or on MC EDRAM, this has to match the off-chip SRAM performance. And we can say that the embedded DRAM consume less power than the static RAM. Here we have an example of IBM Z13 EDRAM cache structure. We have IBM Z13 which used the EDRAM as two-level cache memory, and each PU has up to 8 cores. We discussed about this, and it has a shared of 64 megabit EDRAM on the level 3 cache for the same cache chip as the processor. So these three PU chips share a 4080 megabit of the EDRAM, and we have the level 4 cache memory on a separate storage control chip with a memory related logic. So the level 4 cache memory for the storage control has to include a maximum of 480 megabit, which does not include the cache size as well as the 244 MB NI directory. For this directory, it does store the tags pointing to the level 3, which is on, but does not include the level 4 cache. Here we have the storage control chip layout, which include the level 4 cache of the size of 120 megabit. For that megabit, this size does not include the 56 megabit, which does not include the cache directory. Then we have the level 4 as well as the input-output logic. Level 4 cache controller and the level 4 cache controller, which does not include the cache directory. So about 60% of the storage controller chip area, it is used only for the level 4 cache memory and the directory. The rest of the chip contains level 4 cache memory controller as well as the input-output logic. So this is the IBM Z13 storage controller chip layout. Now, what is the use, the main question, what is the use of the Intel core system, the use of the EDLAM in Intel core system? If you still remember, we have the Intel, which ships product with the embedded DLAM by using the level 4 cache. Level 4 cache EDLAM is accessed via level 4 tags cache stored in level 3 cache of each call of the Intel core system. So accessing the EDLAM requires to go through level 3 memory, then convert the level 4 tags, which has to limit the performance potential. Now we have each core which includes level 1 memory for data and level 1 memory for instruction, and we have this one, level 2 the cache, and we have graphic processor and graphic cache. Here we have level 3, which include level 4 tag, and to go to the EDLAM, we need to access level 3 memory, then convert level 4 tag, which has to limit the performance of the computer system, because whenever the system wants to get access to the embedded DLAM, it has to go to level 3 cache memory, then convert level 4 tags, then get access to the EDLAM. This is the original use of the embedded DLAM memory system. So to solve this issue, Intel has removed EDLAM from its level 4 cache position in the recent product, because it does reduce the computer performance. Now, EDLAM memory has to work as a memory aside rather than a true level cache dependency. Every memory access through the memory controller is checked in the embedded DLAM. On a hit, data is returned from the EDLAM. On a miss, data is allocated and stored there. EDLAM acts as a normal DLAM, or can also act as a DLAM buffer, and it is transparent to the software, the central processing unit, as well as IGP. So this is the use of the EDLAM in modern computer system, especially in modern Intel products. Intel has to remove the dependency between the level 3 cache memory and the EDLAM. Now it is possible to get access to the EDLAM without going through level 3 cache memory, then convert level 4 cache tags, which takes a longer time. Now it is possible to go through immediately to EDLAM memory. Now here we have the use of EDLAM in Intel core systems. Here we have the 8 cores. Each core includes level 1 data and level 1 instruction. Level 1 data, level 1 instruction. Then they have a level 2 memory cache and a level 2 memory cache. And when it comes to the common data, we have a level 3 cache. Then we have a graphical processor, which includes graphics cache. Here we have then different other devices, including the PCI bus system that we're going to discuss when we start with input-output devices and the system bus. We have the system agent. Then we have the cache tags. We have the EDLAM controller. Then here we have EDLAM as a separate memory, and the system can get access to the EDLAM memory without relying on level 3 cache, which can improve the computer performance. Then we have the DDR memory. All right, so this is almost the end of today's class. We discussed about other internal memory. It's just introduction because we want to get the time to go through each and every internal memory as we have done for the cache memory. But we're going to discuss in more details about these other internal memory, including the synchronous DRAM and the DRAM into advanced microprocessor course. So this is just the introduction of the other internal memory. We're going to go through them into more details into advanced microprocessor course. So here we have the synchronous DRAM that we just learned. That does have to use external clock signal in synchronization with the central processing unit, which allows the central processing unit to be aware about how many clock cycle we take the memory to return the data. Then during that time, instead of being in wait time, the central processing unit will be handling other tasks while waiting for the data. So this is for synchronous DRAM. For a synchronous DRAM, it does not provide higher data rate when it comes to input-output devices. That's why there is the introduction of the double data rate. We have talked about the generation 1, 2, and 3, 4, which use a prefetch, and it does improve the data rate using the rising and the falling edge. Then we talked about the embedded DRAM. The embedded DRAM, which was had a dependency with the level 3 cache. To get access to it, we needed the system to go through level 3 cache memory, then convert the level 4 cache memory tag to get access to the embedded DRAM, which had a negative impact on the memory system. Then they need to design and put it into a place to avoid the dependency between the level 3 cache and the embedded system, embedded DRAM, and it can be accessed now without going through the level 3 cache, which has improved the computer performance. So this is almost the end of today's class. Questions? We have done quiz number 8 in this class, right? Right? So get ready for quiz number 9. For quiz number 9, you need to review lecture number 15. Clear? So since we don't have midterm exam number 2 for this course, make sure you do revise all the lectures that we have learned after the midterm exam. Now, get ready for quiz number 9, review lecture number 15. It's going to be anytime soon, this week or next week. So get ready for it. Clear? Your homework number 4 is due today. Make sure you do submit it before the deadline. Otherwise, it will be closed. And also, remember, you need to complete your lab assignment number 5. I'll be checking it in the next lab session. All right. If there is no question, that is the end of today's class. I will see you next class.